Anthony and
Awesome.
Sydney. Thanks a lot. Welcome.
Yeah, thank you so much for having us. And I'll just say right at the outset that if there are any questions that come up as we are going through this, then feel free to just unmute yourself or try to put something in the chat, and we'll try to keep track of that. So it's really a pleasure to be here. I'm just going to give kind of a short introduction, and then Sydney's going to be doing the meat of the presentation. But we're going to be talking about kind of the wide array of techniques that we employ for the verification and validation of safety-critical autonomous systems. And since we come from the aeronautics and astronautics department, we thought it'd be good to kind of start with what I see as kind of a success story in the certification of safety-critical autonomy. And that is with the development of this next generation airborne collision avoidance system, ACAS-X. So on board all commercial aircraft, there are these collision avoidance systems that try to detect possible collisions between aircraft. And if a collision may be imminent, then the pilots are alerted and they can take some evasive action. And these systems have been one of the reasons why flying is such a safe activity. So a number of years back, the FAA was interested in developing the next generation system that's both safer and more efficient in terms of how frequently it alerts the pilots to possible collisions. And our advisor, Michael, was instrumental in the development of this system. And they actually employed techniques from modern AI planning methods as something that was, I think, novel to the FAA at the time. And so there was a big challenge to convince this very risk-averse organization that these systems were actually safe. And it turns out they are significantly, ACAS-X is significantly safer than its predecessor TCAS. And they were able to successfully go through the certification process and make ACAS-X an international standard in 2018. And so I see this as, again, as a really impressive example of taking modern technology and certifying it for safety critical domains. And so in kind of the majority of this talk, we are going to be talking about some of the techniques that were used during the certification process, as well as techniques that have been born out of it since then. And of course, aviation is not the only safety critical application that we care about these days. We also want to be applying autonomous systems in the field of healthcare and medicine, autonomous driving, industrial scale robotics. And all of these domains, one could argue, are possibly even more challenging than aviation. They, can be far more complex and have a more challenging task on hand. So we need to unlock all of this potential by introducing the proper safety validation and verification techniques, as well as the rules and regulations that stipulate kind of what procedures these systems need to undergo before they can be deployed safely. So before we kind of zoom in, I want to talk at a high level about how safety can be incorporated in the design cycle of an autonomous system. So when we go to develop an autonomous system, we typically start by defining a set of requirements. So in the domain of robotics and aviation and transportation, we often think of identifying maybe temporal logic specifications about what our robot should do, or identifying certain dangerous states that we wish to avoid. But we may also consider requirements just based on accuracy or false positive rates if we're talking about a medical diagnosis system. And then we put in some design effort to engineer the system. And this can be through traditional engineering techniques. It can be strictly through machine learning or any combination therein. And we probably want to employ techniques that are, take uncertainty into account and consider the risks of the decisions they make and are generally safe to begin with. But once we've designed such a system, we still need to validate that it is indeed doing what we want it to do and is safe. And so that takes us to steps 3 and 4, where we generate a number of test cases, either through unit testing or scenario generation, or through more advanced techniques like automated testing, and we'll talk about that today. And we use these test cases to ultimately evaluate the performance of our system, either maybe estimating the probability of failure or the false positive rate. And if we meet our requirements, we can perhaps deploy that system. And if not, then we have to go back and understand the ways in which the system fails and perhaps do some, redefine our requirements and the cycle repeats. In this talk, we're going to just zoom in on this portion of the design cycle, where we assume that we already have a system on hand, and then we're going to ask the question, how do we validate the safety of this system? And so we're going to go through kind of a wide array of techniques that a little bit blur the line. So we're primarily focused on evaluation, but we can think about, some of the techniques we might use during a tighter design loop, as well as techniques that might be deployed kind of immediately after we've decided that our system is safe in terms of monitoring it at runtime. So one of the first things you might do is just some really basic, straightforward sampling. So you've designed your system. Let's run it on a few sample test cases, make sure that it works, or get a set of test data and see if you're making the correct classifications. Then there are kind of more advanced techniques like falsification or most likely failure analysis, where we actually actively search for failures. And this can help us uncover the more rare failure modes of our system. Then we can use the discovered failures to try to estimate the probability of failure. And this is getting closer to maybe where we would certify the system. We might try to employ techniques from formal verification, where we actually get provable guarantees about the performance of our system under a set of assumptions. And then lastly, we might do some amount of uncertainty quantification. So at runtime, we try to figure out when we are violating our assumptions and we know that something unsafe might happen. So now we're going to go through each of these techniques, and we're going to do it using a specific example from aviation. And so I'm going to pass it over to Sydney, and she's going to walk us through it from here.
Great. All right, so I'm going to go through kind of how we test a very specific AI controlled system that we use as an example a lot in our research in our lab. But hopefully, even just looking through this specific system, you'll be able to see some parallels to the domains that you work in and maybe find some interesting techniques you could apply. So I'll start by just defining the problem that we're going to be working with. We'll assume that we have an aircraft that's situated somewhere on a runway. And then we have a controller that's part of our system design that tells the aircraft how to successfully steer itself down the runway. And in order to do this, the controller will need a few pieces of information that give it the position of the aircraft. So for example, one piece that we use is the cross-track error, which is how far the aircraft is laterally from the center of the runway. And then also just the heading error, which tells us how many degrees of angle we are off from just facing straight down the runway. And so taking both of those inputs, our controller can then output a steering angle. But there's one extra problem here, which is that we can't just automatically know our cross-track and heading error. We don't just automatically know our position. And in these real-world systems, we need some way to actually be able to sense it. So there's various sensors that you could use. But in this work, we're going to assume that we use a camera as our sensor that's mounted on the wing of the aircraft. And it can continually take pictures of the runway, and then we can design an AI-based perception system to take those pictures in and then output an estimate of our position on the runway. And so that's where the AI comes into the system. And then we'll come up with just kind of an example specification that we might want to test our system against. And in this case, we'll come up with a kind of very simple specification that's just the aircraft must never leave the runway. So it should never, this controller should never steer it in a trajectory that causes it to veer outside the lines of the runway. And so now I'll go through how we might apply all of these techniques that Anthony kind of overviewed at a high level to this specific system. So we'll start with sampling. And this is, as Anthony mentioned, just kind of the first thing you might try once you have a design for your system. Just try it out in a few scenarios and see how it goes. So let me explain what's going on here. In this upper left image where it says original image, this is the image that the aircraft is seeing from its camera. And then we take this image and we downsample it, meaning that we just kind of crop out the sky and pixelate it a whole bunch. And that's just easier. It just makes it easier for our AI system to do the steering. So this is the image that actually gets fed into our system. And then you can see this is the trajectory that the aircraft follows over time. And the pink dots just show the position that got estimated by our perception system. So you can see it's doing pretty well. It kind of goes towards the center of the runway and then starts to stay there. And we can test it for more than just this specific scenario. We can try a whole bunch of different starting states and initial positions along the runway and then see how it performs. It seems to do pretty well. None of these trajectories veered off the runway. We have a pretty good indication after doing this sampling that maybe our system has a chance at satisfying our specification. So just to summarize the sampling technique, the pros here, it was a really quick way for us to debug the system. If we saw that it didn't even handle these very simple test cases, we probably need to go back and redesign. And since it does seem to handle these, we have at least now an indication that our system might satisfy the specifications. But of course, we just kind of tested over a set of nominal scenarios that we could think of. And so we probably didn't find all possible failures of the system. And just seeing that it works in these cases doesn't mean that it's always going to work. So we don't have any guarantees here. And so with that in mind, we now might want to move on to saying, okay, can we like stress test the system a little bit further? And instead of just sampling over some nominal scenarios, let's see if we can really test it to its limits and find various failure scenarios. So I'll kind of combine falsification and most likely failure analysis in this presentation for this specific example. And I'm going to highlight some work that was done by a student named Kyle Julian, who's an alum of our lab, on essentially doing this type of thing for the taxi problem. And before I do that, let me just talk about how we could kind of create a failure for this system. So we have our system here, and we can think of it as kind of taking in this small image of the runway. It goes through our perception system, through our controller, and the final output is a steering angle. And if we wanted to create a failure for this system, one thing that we could do is we could actually inject some noise into this image and assume that we're getting some noisy image from our camera. And then this image, we could feed instead this noisy image into our perception system. And that's going to output a slightly incorrect steering angle. It'll output something different for the way we should steer our aircraft. And what we can do is we actually have techniques. And if you're interested, you can ask after or offline, and we can explain more how this works. But essentially, we have a way to be able to, given a noise budget, how much noise you're allowed to add to the image, we can find the maximum error that you could possibly get for this like steering angle output. And so one thing you might think to do to try to find a failure where the aircraft veers off the runway is you could just say, okay, let me just apply this maximum error, this worst case error, in maybe like one single direction. So in this case, we're saying let's apply the worst case error to make it turn left more than it should, over and over and over again, and see if we can get our aircraft to slowly keep moving to the left and then veer off the runway. So these are the perturbed images that the system is seeing, and this is what it's doing. And you can see we're kind of getting close. We're moving the aircraft to the left, but we still haven't actually found an official failure according to our specification, because the aircraft never veered off the runway. So this actually wasn't enough. This kind of simple analysis was not enough to actually find a failure in our system. And so this kind of motivates maybe a more complicated technique that is able to kind of mix up these types of disturbances. Say maybe one time we try to disturb it to move to the left, and then the next time step we try to disturb it to move to the right, and we can kind of mix these up in a smart way to maybe find a failure. And that's the hope here, and that's kind of what we could use something like adaptive stress testing for. So adaptive stress testing was also developed in our lab, and it's essentially a technique that uses techniques from reinforcement learning to find failures in sequential decision-making systems. So applied to this specific example, we use adaptive stress testing to try to select a sequence of these perturbations, either left perturbations or right perturbations, that could actually cause the aircraft to leave the runway for a given noise budget. So here's what happens when we give it a noise budget of 0.02. You don't have to really worry about the exact number of the noise budget, just know that lower will mean that it's less noisy images that are allowed. And so here in this case, you can see this is kind of showing the search tree, or the search of trajectories that this adaptive stress testing technique went through in order to try to find these failure trajectories. And you can see that all of the trajectories that it tried out, there's a whole bunch here, never veered off the runway. They never left the runway. So this might give us some confidence that for noise of 0.02, we don't have any failures, but we can't say for sure because we've never tried, we haven't enumerated all possible scenarios. However, as we increase this noise budget, we allow our images to be a little bit noisier when we input them to the controller. We're actually able to find some pretty interesting failure trajectories. So essentially in this case, we found that if we give it a whole bunch of left disturbances for a while, but then all of a sudden we switch it and say, okay, now move to the right, or we try to disturb it to move to the right as much as possible, it gets into some kind of weird configuration where it's kind of facing straight off the runway, and the system's never seen anything like this before, and it causes it to just kind of drive straight off the edge of the runway. And so using this kind of more complicated adaptive stress testing approach, we're able to find some more interesting failure cases. And then as we increase the noise, you can get different types of failures, and maybe we could also get it to fail faster, like veer off the runway faster. And here's just an example of what one of these failure trajectories look like. So you can see it starts with applying right disturbances actually here. These again are what the perturbed images look like. And then as it keeps going, it starts to turn now. Now it's in kind of this weird configuration where it's headed straight for the side of the runway, which it didn't see very much in its training data. And as we keep going, it now is kind of just headed for failure, and it's going to veer straight off the runway. Okay, and so this is just a very specific example of applying adaptive stress testing in this case, but there's also lots of more interesting or other interesting ways to validate black box systems. And actually, Anthony and a few others in the lab wrote a wonderful survey paper on this. And if you're interested in learning more about all the different ways that you can try to find interesting failures in systems, highly recommend checking it out. And so the citation's at the bottom of the slide here, and it goes through all of these different techniques to do this type of analysis. So summarizing this type of analysis, the pros are now, instead of our sampling over nominal trajectories, our initial sampling, now we've done a lot more stress testing of our system, and we can find some rare failure events. And we can use those now if we wanted to go back to the design step to redesign our system or improve it in certain areas. And these techniques, it's really nice, a lot of them are available for black box systems. So if you have a really complicated system that can be otherwise really difficult to kind of dig inside and analyze, you can just treat it as a black box and apply a lot of these techniques and still find really interesting failures of your system. So it also helps with scalability. And then some of the cons is we did find some failure events, but we may still miss some rare failure events. So for example, if I go back to this slide where we saw delta equals 0.02, for this particular noise level, we weren't able to find any failures. That doesn't necessarily mean that there's never a sequence of noise disturbances within this for which it would fail. We have maybe slightly higher confidence that that's the case, but there's no guarantee here that if we ran this for longer or had some other type of optimization, we wouldn't find a trajectory that does violate our specification. So again, there's no guarantees here. Okay, so moving on from that, now once we've kind of maybe gotten some of these failure modes out, removed some of the bugs of our system, we can move on to something a little bit more extensive for an analysis, such as formal verification. So what formal verification does is it is able to give us an actual guarantee, given some assumptions.
I think we have a hand raised.
Oh, yeah, feel free to just unmute.
Ajitha?
If there's a question.
Sorry, I joined your talk a little late because I was caught up in another seminar. So from what I've seen just over the last 5 minutes, you said you cannot catch certain rare occurrences, but it's better than simply perturbing the system. It's better at catching some occurrences maybe. So typically rare occurrences are those that are deep in the state transition system or in your decision-making system, something that's embedded deep, right? Why is this, at least in the testing world, we combine it with some sort of symbolic execution to catch these rare occurrences that are embedded deep in your system, deep inside your state system. How does this catch such faults? How is depth handled? I see that if you increase the noise, sure, you have more possible paths and transitions that you can take, but it doesn't really guarantee. I know you said it won't guarantee that you find deep faults, but I don't even see why it's more likely to catch faults that are deeper in your state system or your decision-making system.
When you say deep, do you mean like further into the trajectory?
Along the sequence to get to that.
Yeah. Well, so typically we have some like auxiliary signal, like a temporal logic robustness or something that's guiding it. So we use like in that example, we're using Monte Carlo tree search with a reward function that was related to, for example, the robustness of our specification. So there's kind of like a notion of getting closer to a failure that maybe allows you to find sequences that ultimately lead to failure.
So how would you quantify closer to a failure based on your specification? So either the specification is satisfied or it's not satisfied. What does closer to a falsification of a specification even mean?
Yeah, so are you familiar with like the work on robustness of specifications?
No.
Okay, so there's this notion, especially with like signal temporal logics, where you say, for example, in our runway case, where you say, okay, the aircraft should never leave the runway. What that really means is that the cross-track error should always be less than 10 meters, or like the absolute value of the cross-track error should be less than 10 meters.
Okay.
So what you can say is like the robustness is kind of like how close were you to 10 meters? If you were 9, then that's real close, and if you were 11, you were over it. Yeah. So
you have some notion of boundary.
Yeah. And you can kind of derive this in general for like signal temporal logic. You can get a smooth-ish notion of closeness to a failure, especially in like a time-bounded setting.
And that's used as a heuristic to guide your search.
Exactly. Yep.
Okay. All right. Okay. Thank you.
Great. Okay, let me just go back here. Okay, so yeah, we're going to move on now to formal verification. And in this case, we actually can try to get some guarantees. And essentially, we do have to input some assumptions, though. So the first thing that we'll input to these formal verification techniques is our AI system. We also need to input some sort of property for it to either say, yes, you satisfy it, or no, you didn't. And then we need some input set to say, okay, you satisfy the property, but with respect to this possible set of inputs to your system. And then what it will give us is either a check mark or an X. Yes, you satisfied this property. No, you didn't. And so in our case, for the taxi problem, our AI system is just the taxi control system. And then the property will just be our specification that the aircraft must never leave the runway. And then in this particular application anyway, where the challenge really comes is in specifying this input set. So if you think about it, our taxi system takes as input an image. And in fact, it's actually one of those downsampled images. So really, we take in 8x16 grayscale images. And we need to describe, in this case, what is the input set to our controller. So we could just say, okay, well, let's just verify over any grayscale image that's 8x16. But that's the space of all possible grayscale images. So like, for example, this smiley face, if that gets input to our taxi controller, we don't really expect it to work, right? And we don't ever actually even expect to encounter that type of image during operation. And so what we're actually interested in is a much smaller subset of this space, which is the set of images or the set of inputs that look something like a runway. And I would challenge you to try to just like write down what this set is, and it's much, much harder to quantify. It's not obvious how to write down what is the set of all images that look like a runway. And so one of the solutions that we came up with in some of our recent work was to use a generative model to capture this. And if you're interested in the specifics of this, I would highly recommend checking out the paper. I won't get into too much detail, but essentially we can use a generative model to try to capture this space of images that look like a runway. And then there's also some recent work that we just wanted to add to the slide in case you're interested in checking out these papers after the fact. I won't go into much details, but we did it in a slightly different way in another work that involves like over approximations of forward models that if you're interested, you should definitely check out. So replacing now our input set with this generative model, we now have everything we need for these formal verification techniques. And if you're, by the way, you're interested in the specifics of those, I would also recommend checking out the paper. But essentially, just as an example, this is the type of thing we can get out, where this says for every state in our state space, so for every possible cross-track error on this axis and heading error on this axis, we can find out if we were to start in that state, so if we were to start with that given cross-track and heading error, we have a formal guarantee now that we will never leave our runway. We will always in gray states that are gray, we will always satisfy our specification. And you can see, like in this case, the states along this axis here, where the heading error is 0 and the cross-track error ranges between -10 and 10, we can basically show that if we start at a state where we're somewhere on the runway and facing straight down the runway, in the future time steps, we will never leave the runway, according to the input set modeled by our generative model. And again, if you're interested in more on how these things work, a lot of that work was enabled by these recent development of algorithms for verifying deep neural networks. And there's also a great survey paper that came from our lab that describes this and goes into this really well. It looks like this. It's super nicely done, and the citation is here. Also, if you're just interested in learning about neural verification, neural network verification at a very high level, and maybe you've never heard of it, or you just want to get an idea of what it's doing, I recently made a nice intro YouTube video explaining it that I would highly recommend checking it out. And to summarize here, the pros of formal verification, again, is that we can actually get this nice guarantee. We can say, for all possible scenarios, according to our assumptions, the specification will or will not be satisfied. But then again, some of the cons, we had to make some assumptions about the inputs. Sometimes there's other assumptions you have to make. And also these algorithms that I mentioned for formal verification, they can be quite computationally intensive. So it can be a little bit difficult to scale to large systems. And of course, the state of the art is always improving. But as of right now, we can only apply them to somewhat smaller domains. And then finally, once we've done kind of all of these tests and we're like, okay, it seems to work in this case, under these assumptions, we formally verified that it worked. Now, when we get to actual runtime, we might still want to go one step further and say, maybe we should try to also identify scenarios in which we haven't tested or when it's in a situation that we haven't seen before. And so that brings us to uncertainty quantification. And so I just want to mention a scenario here that we haven't tested. So we tested kind of nominal conditions. We formally verified that this thing will never leave the runway. We looked for some failures and found that for some extreme levels of noise, we could get it to leave the runway. But here's one thing that we actually never considered in our previous analysis. So you watch the aircraft, it's going pretty well right now. But eventually, this aircraft actually gets to a point in the runway where another runway crosses over it. So the lines have completely changed. It's never seen images like this. And you can see that as the aircraft keeps going, it just starts to kind of veer off to the side and totally almost turn down the other runway. And it doesn't follow its centerline tracking anymore. And it does veer off the side of the runway. And so this could be potentially dangerous. And what we might prefer in this case, we can't ever say we'll account for every possible scenario we'll ever see, but maybe we could at least identify that the aircraft could say, hey, I'm in a situation where I've never seen before. And instead of veering off to the side, it could enter a safe mode or stop or have a pilot take over or something like that. And so that's kind of the motivation behind some of these uncertainty quantification techniques. You might also have heard them called like out of distribution detection techniques, which would be more of like a binary, like, yes, I've seen this scenario, or no, I haven't. And essentially what they should be used for is to identify when they're in scenarios that they haven't been trained or tested on through some metric of uncertainty. So here's just a really simple kind of classic uncertainty quantification technique applied to this type of problem. And you can see I'm plotting essentially the prediction of the state here, the prediction of where the aircraft is, with some error bars around it, because now we've quantified our uncertainty in that prediction. And then you can see as we get to this runway crossing, our error bars get much bigger, and we're able to actually identify the fact that we haven't seen states like this, and that maybe our controller is not going to perform the way we want it to. So this can add kind of an extra layer of protection at runtime after we've done all of our testing. So some of the pros with this, like I just said, you can catch these potential issues at runtime. And so you can kind of correct for things that maybe you missed during your testing. And this allows then, if you have some system for a safe mode, or if you have some ability for a human to intervene and take over, it can flag that for someone to take over. But some of the cons, and one thing that I think is like a really interesting challenge coming up, is that it's really hard to be confident that these techniques will correctly flag all out of distribution inputs, or will correctly always say that they're not confident in scenarios they haven't seen before. Because it's really hard to say like, okay, for every possible thing that could happen, I'm definitely going to say that I don't know what it is. It's really hard to test that systems will do that, and it's hard to design systems that will do that. So just wrapping up, we've gone through a whole bunch of different techniques and kind of outlined the pros and cons. And what we really want to emphasize, though, is that, as many of you may be already thinking, this is going to really be a combination of these types of techniques that gets us to actually be able to certify systems like this. So you might be familiar with like the Swiss cheese model, which says like there might be holes in some of these techniques, but if we kind of stack them all together, hopefully nothing will get through. And so ACAS-X relied on quite a few of these techniques to make the safety case for certification. And hopefully, as we continue to improve these techniques and design some regulations to go with them, we can also get there with some of these more complicated systems. And so we'll just wrap up. This is a picture of our lab. Here's Michael on the left, and Anthony and I are in here, and some of the others that did the work in this presentation are also in here. Here's our lab website. Here's the website for the Stanford Center for AI Safety, along with our email addresses. And we're here for 2 more days, Thursday and Friday. So if anyone's interested or wants to talk more, we're super happy to meet and discuss any of this. So yeah, thanks so much for listening, and we're also happy to take questions now.
Sorry, I was muted. Thanks very much for that, and maybe a round of applause is a good thing to do. There we are, lots of applause. And do we have any questions? So we'll look at hands. So Jita, is that a legacy hand, or are you going to ask another question?
I have another question.
Good show.
If I might. If anyone else has, feel free to go. So I was wondering, so in your examples, obviously you've limited yourself to specifications where you only have 2 variables, the steering angle and what was the other thing, distance, I'm not really sure, maybe the width of the runway. But you haven't really accounted for the environment and other aircrafts potentially. And I was wondering if there was work also done into considering the environment model in your work, both whether it's in falsification or formal verification, uncertainty, quantification, all of that.
Yeah, that's a great question. Thank you for it. I'm just going to go back. So the one place where we have emphasized more, spending time more with the environment model is in these falsification style techniques, because of their scalability. So this kind of this little diagram, I think it kind of explains it well. The way we kind of do falsification is that you have your system under test, which you can kind of treat as a black box, but it's operating in some environment, and the environment has its own dynamics. Maybe it has other actors that are interacting with the agent and each other. And so there's potentially a lot going on, which you have to spend a lot of time modeling to make sure that it actually is representative of the case that you have. And then we have sort of some adversary, which is like the thing that's trying to find the violations of a specification, and it can control the environment through some disturbance. And so this disturbance can be, for example, the behavior of other aircraft on the runway or pedestrians in a driving scenario, or things like noise in the perception system or whatever. So it's really anything you can kind of gain control of that would influence kind of the overall behavior. And so then your specification is really over like the state of the environment, which includes both like the system's behavior as well as the other agents and things interacting. And so anyway, that was kind of a long-winded way of saying yes, we think about it for the falsification case, but it's a bit harder in the formal verification case just due to scalability problems with as soon as you start.
Yeah, but that's what we always do in the formal verification world. We always box this environment into a model that we don't really know about, but we will get information off of. But that is a hard problem in the sorts of systems that you are considering. It's an important problem, but I understand it's very challenging as well.
Yeah, and actually we didn't mention too much here. I don't know if Michael's still in the chat. He might be able to put some links in the chat there, but our lab has another thread of work that's all about modeling, for example, pedestrian behavior or other driver behavior from data, just to build up these models of the environment to use for testing and things of that nature. Yeah.
Okay. All right. Thank you.
Okay. Do we have any other questions? Ajita, your hand's still up. Have you got another one?
Sorry, that's a hand that I need to.
That's a legacy hand. Oh, it's gone up again. Yeah. Okay. Anybody else? Yeah. Otherwise, I'll ask questions. Yeah, that's a threat more than anything else to the other attendees. Yeah. I've got a very general question actually that came right from the beginning. So this is kind of addressed to Anthony. Yeah. Sure. I mean, back at the I mean, these are your opening comments. So this isn't really about a technical thing. It's about the definition of efficiency. You said that this is more efficient. Yeah.
Oh.
And you also said it's safer than its predecessor in some sense, or you were talking about systems doing that. And I wondered, I mean, what's the measure of efficiency? Because certainly in work that we've done, the predictability of warnings for people who are human operators, for example, is probably more important than, say, simple measures like the frequency that you get warnings. Yeah. And so it may well be that a system which warns rather a lot, yeah, and so may by some measure be seen as being inefficient, actually makes life safer, because actually the human user is more vigilant or is able to anticipate when the warning is going to come. So I wondered what you meant by those remarks at the beginning, or whether they were just kind of off the cuff introductory remarks, and I should just ignore them.
So I'll say what I meant, and then I'll let Michael maybe jump in and add something. So yeah, I was merely referring to the rate of alerts, like that was it. So there's a lower rate of alerts with ACAS-X than TCAS, and we see this, you know, as a good thing, so that it doesn't, you know, panic the pilot or whatever, while also still lowering the safety under those models of human interaction with those alerts. But Michael, maybe you can say more about the human factors side of things.
Yeah,
I had a quick follow-up that Michael might want to cover as well. Did you talk to the pilots about it, and what did they say? When we talked to neonatal people, for example, in a neonatal intensive care unit, they didn't want to have less frequent alarms because they had a work rhythm and the alarms prompted them. But that might be very different for a pilot.
Yeah, it's a bit different. And I should also clarify that there are a couple different layers for both TCAS and ACAS-X. There are both traffic advisories where the system says, you know, traffic, and it prompts the pilots to start looking out the window. There will be an indication on their display of the relative position of the other aircraft. Pilots love these traffic alerts. Where ACAS-X was aiming to become more efficient is at the next layer, where there's a resolution advisory. So the resolution advisory instructs the pilots to climb or descend at a particular rate. And this is actually quite disruptive, right? And you want to reduce that rate for a few different reasons. One is it's disruptive. It could be disruptive, like if you're approaching an airport. It would result in an unnecessary maneuver. And also there's the downstream effect of committing you to a particular direction that might not be what you want, depending upon how the encounter evolves over time. It may result in having to do a reversal, changing the direction of the aircraft. And when you have, you know, a couple large planes converging to each other, you don't really want to mess around so much. We did. Yeah, sorry, go ahead.
And these would be done entirely autonomously. A controller wouldn't be involved. The ground controller wouldn't be involved. It's just entirely within the aircraft. Yeah, is that the idea?
It's within the aircraft. There's some divergence between Boeing aircraft and Airbus aircraft. Airbus has an automated response. Boeing requires the pilot to disengage the autopilot and hand maneuver the resolution.
Okay.
The air traffic controller doesn't have any control over this, but the procedure is such that it's up to the pilots to call out that they have that they're following a resolution advisory. And the recommendation of TCAS, especially after the Uberlingen collision, is to follow what TCAS or ACAS-X instructs over the instructions of the air traffic controller. And the reason for that is TCAS and ACAS-X, they coordinate between aircraft at high frequency. And so it always ensures that there are complementary maneuvers. So you never want both aircraft to be climbing or both to descend, which is what happened with Uberlingen.
Yeah, and you have to be, presumably they have to advise the controllers, because when they're making a disturbance, that may affect other aircraft. So that comes back to a Jesus.
That's right. Yeah, there's a lot of consideration about like downstream effects here. And we went through a number of very in-depth simulation studies, as well as flight tests. And yeah, so the development of ACAS-X started in 2007. And as Anthony mentioned, it didn't become an international standard until 2018. Vast majority of that time is just going through extremely rigorous verification and validation, all forms of rigorous assessment across the world by different labs, and everyone cross-checking each other and so forth.
Okay, good. Okay, so I have at least one. I mean, I have many more questions, but I'll ask one more, unless somebody else wants to ask a question. Anybody else got a question they want to ask? Ah, Craig.
Hello, can you hear me?
Hello. Yeah,
Hi.
we can hear you.
Yeah, thanks for the talk, guys. I was actually just curious about at the end of your presentation, you touched on uncertainty quantification, and you were saying that you had this thing where you're saying like, oh, well, you know, what we can possibly do is find areas that are out of distribution, and then hopefully the system will have high uncertainty in those regions, and then it can sort of say like, I don't know what to do here, like someone needs to take over and things. But then you had this kind of like, who watches the watchman problem at the end, right? Where you're saying like, well, how do we know that it's going to give low confidence in those out of domain areas? Like, it could just be highly confident for things it hasn't seen. And so that sort of sounds like a kind of model calibration question. And I was wondering like, what kind of work, like if any of your lab has done kind of work on like, you know, verifying that like this out of domain distribution stuff is actually low confidence or something like that.
Yeah, that's kind of, I think that's like a big challenge right now. Like to me, that seems like one of the biggest challenges with this stuff. And if you can somehow make some progress there, I think that'd be like a really awesome contribution. And so I've been like sort of thinking about it, but I haven't made any tangible contributions on that yet. I don't know if you know of any.
Yeah, no, I mean, a lot of the techniques that exist, you know, will basically choose an in distribution data set and then maybe one or more out of distribution data sets, expose you know, their neural network to the training data set with the corresponding techniques for uncertainty quantification or OOD detection. And then they just say, okay, hey, look, it on these other data sets, it seems to have high uncertainty. But of course, that's like a really small set of samples of what could possibly be encountered in the space of out of distribution, because that's just everything else in the world. And so, yeah, I don't even think that there are like standard benchmarks that are good that demonstrate this problem. I think it's been all a little bit ad hoc.
Yeah, I guess that was what I was curious about. It's like, what would it even take to like convince you that like your system was well calibrated in these out of domain things? Like in an ideal world, what would you want it to say or guarantee, I guess?
We could almost do like a reverse, like we use that generative model to say, you know, like all the images that can be generated by this generative model produce good outputs. Wonder if you could try to do the reverse, which is every image that can't be generated by this generative model will give high uncertainty or something like that. Kind of like flip the query around, but I think that'd be quite the challenge to have design a system that was true for.
Yeah, and I think like one other way you could do it is like, you wouldn't this wouldn't give you any guarantee that it'll work, but you could be more confident if it seems like your system kind of understands what's going on. So for example, like there's certainly out of distribution inputs that are more challenging to detect. So for example, if I had a picture of the runway and then I just kind of covered up one of the lines a little bit, the rest of the picture still looks pretty similar. So a sort of naive out of distribution detector might miss that. And so I think like you could have at least more confidence if it maybe worked on more what you would define as like more challenging out of distribution inputs. But then of course you have the issue of deciding what's challenging, but something along those lines.
Cool, thanks guys.
Okay, Robin. No, you're muted, Robin. Still muted. Yeah, okay, you're on now.
Yeah, hi, Stuart. Could you say something about how you leverage the formal verification in the uncertainty quantification? Because it seems that you can do a lot of really clever analysis, which might tell you a bit more than just testing your out of distribution stuff.
We haven't tried that to answer it simply, but I guess one thing, it is kind of interesting, and one thing we thought about is like with this formal verification, we had to quantify this whole set of inputs that look like a runway. We do have a quantification of it. What is the distribution that we expect for? So it does feel like we could do something with that, but we have not.
Okay.
Thank you.
Thank you. We still have, no, that's Robin's hand. Is it any more hands?
I think Ajitha had another question.
Oh yeah, she does. Yeah, yeah. Okay, Ajitha.
So I was just,
yeah,
so there are notions of coverage defined in the literature, but it's mostly over the neural network model itself. And I was wondering, when you use your GANs to generate interesting inputs, do you have a notion of, obviously the features within the GAN can be used to define coverage, but do you have anything beyond that that's independent of the GAN itself to check whether you've generated enough input scenarios or images?
So one thing that we did do in that work was we kind of realized that our guarantee that we provide is only going to be as good as essentially the coverage of our GAN, like how much of our input set were we really able to capture. Or sorry, I said GAN, that's what we used as our generative model. And so we came up with a sort of recall metric that says like how much of, given a data set, like how much of our data could we actually produce by this generative model, and use that to be able to compare different generative models and figure out which one was actually capturing the input set best. So it's not quite the same as these like neuron coverage metrics, but that's as close as I can think of that we've tried to what you're describing.
Ajitha, you're muted again.
The classic problem. Anyway, I was thinking more in terms of specification derived coverage metrics that you can check with respect to your generative model, the images from your generative model, how well they cover either the specification or any input scenarios that you can derive from your specification. So that would make it a bit more, that would separate out the realization of the model and the testing itself and checking how well you've tested.
Yeah, I think it's a really interesting idea. I think since our case was very simple, we had, essentially a conditional GAN where we input the state on the runway. And so our input set over the variables of our specification is just like a rectangle of like, the cross-track error and the heading error. And we just kind of made sure we covered that space adequately. But yeah, something that was maybe a little more complex in a more complex problem, having a notion of coverage on the input of the generative model would be really interesting. But yeah, we hadn't thought much about it.
Okay, thank you.
Okay, I think we've got time for one more question. Anybody else? Otherwise, I might ask it. Okay, so this is just something that just occurred to me when you were talking. I mean, the traditional safety critical systems, you worry quite a lot about component failure, yeah? and typically you might think about fault tolerance and so on. And I was just wondering how kind of consideration of fault tolerance interacted with the sorts of verification and validation techniques you're looking at, and the extent to which you considered it. Because usually you get some kind of slightly horrible combinatorial thing arises when you start to do that kind of thing.
Yeah, that's a fantastic question. And the answer is that we've, I think, tried to evade that problem in some respects. So, the neural network verification work is focusing on finding failures of individual components or of simple closed loop systems. And then this work on black box safety validation, which I think is still up on the screen, is kind of meant to say, okay, well, your system is composed of a bunch of different components, and we're just going to look for failures of the totally integrated system in a black box way, and we're not going to consider the interaction. So we kind of skirt around it in both cases. However, some of the work that we've been working on here in Edinburgh, as well as some work being done at Stanford through that NASA ULI initiative, is beginning to think about, how you can look at the failures that you can identify in individual components and either make statements of safety of an integrated system or find, use it for falsification and find integrated failures. But it's not a lot of work that we've done.
I mean, I suppose, okay, so maybe just as a follow-up, I suppose that the thing that I started to wonder about was whether, if you looked at the safety case for something like a lane keeping system, which is kind of good old-fashioned AI, maybe not even AI, and what you've got here, might be kind of interesting, because then you'd have, if you like, almost a pre-constructed safety case along the classical safety case situation, and then you could maybe look and see how that contrasted with the sort of case you might want to make. Yeah,
that's a great idea, actually. That would be something cool to look at and see with where each of these techniques might fit into that existing safety case.
Okay, so I think we should let you go now, and maybe we can give you another round of applause and say thanks very much, and let's hope that things are fruitful in terms of future collaboration between here and Stanford. That's great.
Absolutely.
Thank you
again so much for having us. It was great.
Thank you.